In the last presentation, we got an introduction to AI agents. And in this presentation, we will learn about a few popular foundational patterns that are used to build agentic AI systems. Patterns provide a structure to how an agent plans, acts, and collaborates with other agents. And I think a good way to learn and to build an intuitive understanding is to see example implementation of each of these patterns. Therefore, I have created simple Python functions to demonstrate each of the patterns that I will cover today. However, most popular frameworks, including LangGraph, provide built in support for many of these patterns. So, in real world implementation, you may not need to write custom code to the extent that I'm showing you in this lab. Also, agentic patterns are not mutually exclusive. In fact, most real world agent implementations combine multiple patterns together, which complement each other by addressing different aspects of agent behavior, such as reasoning and planning, routing, multi agent coordination, quality improvement, etc. Let us go over some preparation steps before we explore the patterns. As a first step, I'm importing some basic Python libraries. We need a large language model for agents reasoning and content generation. I'm using Boto 3 to create a Bedrock runtime client, and we will use Amazon Nova Pro as the large language model. We also need an embedding model to create vector embeddings for example documents in the knowledge base that our agents will dynamically retrieve. And I'm using Titan embedding model for that. Here I'm defining the call underscore LLM function for making the large language model inference call. Throughout our lab, we will use this function to make large language model calls for reasoning and response generation. This is a standard implementation of Converse API using Bedrock Runtime Client. The key thing to notice here is that temperature is set to zero point 0.2 as default. This is because we want highly deterministic and fact based responses, as the model will act as reasoning engine for our agents. Here we are creating a function to invoke the embedding model using Bedrock Runtime to create a vector embedding for the text. I've created a mock knowledge base so that our agents can retrieve context relevant to the task they're trying to solve. And I have created many documents where each document is basically a title and a line of text. So, this refund policy will be retrieved many times in our agentic implementation, and it reads standard refunds allowed within 30 days. Platinum customers may receive exceptions with manager approval. One example has AI trends and AI investment trends. Now I'm embedding these documents and saving them in document underscore embedding list. And I'm using it to retrieve these documents at runtime by matching them with the query text. Also, I've defined cosine similarity to measure similarity of vector embeddings with the query text. And I've defined this retrieve function to do the semantic similarity between the query text and document embeddings. Notice we are always returning the top two matches for every retrieval. Agents do their actions by invoking tools, and for that, we have defined two tools in our lab. One is the lookup tool, which basically provides an abstraction over the retrieve method. So, this tool will retrieve documents from the knowledge source, and we have calc tool, which will evaluate a mathematical expression. We need to pass descriptions of the tools to the agents so they can reason over the problem and decide which tool to invoke. For that, we have created this tools description text, which basically has two tools: search tool, which is the retrieval tool, and the calculate tool with a description of each. And then we have a mapping of search to the lookup tool and calculate to the calc tool function that we have created. And as a last step in the preparation, we have defined classes to observe agents' reasoning and execution flow. We have defined a step class with actor, action, and output. And then we have a trace class which has a list of steps, and we can add a step and show all the steps. So throughout our lab, you will see we show all the steps that agent has taken in its reasoning and execution flow. All right, so we have covered the preparation for the lab. Now let's learn about the agentic patterns. The first pattern that we will learn about is the React pattern. This is one of the most widely adopted agent designs as it combines reasoning and action in an iterative loop. The agent reasons about the problem, it decides whether a tool is needed, executes the tool, observes the result, and then continues reasoning based on the new information. This pattern of reasoning and acting is repeated many times till we either achieve the goal or we iterate the maximum number of times. React pattern forms the foundation of many modern agents because it allows the model to dynamically decide when and how to interact with external tools and systems. Let us see an example implementation of this pattern. In this function that simulates a React agent, we get a question or goal for the agent and maximum number of reasoning and action loops that we can have, which is 5 in this case. The first step is to define the trace object for recording the reasoning step, tool call, and the result of the agent. This will help us observe agent's behavior. Next, we define the prompt that instructs the model to follow the React format by returning its thought, choosing an action, receiving an observation, and eventually providing the final answer. Notice we are also sending tools description and question in this prompt. State acts as agent's temporary working memory, and it contains the original question in the beginning as we are setting it to the prompt value. And over time, it contains the observations that are gathered as a result of reasoning and acting multiple times. Now we enter the loop, which is the loop of thought, action, and observation. And as a first step, we call the large language model with the current state. Model reasons over the current state and comes up with either the final response or requests a tool to be executed. If there is final in the response, that means we have the final answer. We break out of this iteration. Otherwise, we extract the tool name and the arguments from the model's response and then call that particular tool. We add the response of the tool to the state. So, this way, we have state as the ultimate record of all the information we have gathered. Let us call this agent for this query, which is can platinum customers get refund exceptions? In the first iteration, we see that model had a reasoning to answer the question about whether platinum customers can get refund exceptions. I need to search the knowledge base for relevant facts. And then it also gives us an action to call the search function with this query string, which is basically the original query string that was sent to the agent. So we execute the search and we get these two responses, which are two documents. And if you notice, the first one is very relevant to our query. It says standard refunds allowed within 30 days. Platinum customers may receive exceptions with manager approval. So in the second iteration, the model reasons based on provided observation, it is indicated that platinum customers may receive exceptions with manager approval. This directly answers the question and it provides the final answer. So in the React pattern, we saw how we passed the problem and tool description to the model, and it dynamically made a decision to invoke a particular tool and then produce the final answer in the next iteration. The next pattern that we will learn about is reflection. which, as the name suggests, introduces a feedback mechanism that helps improve the answer's quality by identifying mistakes. Here, an agent performs a task and then critiques its own output and then attempts to improve the result based on the criticism that it receives. This pattern is particularly useful for complex reasoning tasks as it improves answer quality, but it does add latency. Let us look at an example implementation of this pattern. So here in this function that simulates an agent that implements reflection pattern, we have a task to complete. And as a first step, we send this task to the large language model to generate the first draft response. We use this draft response to criticize it in the second call to the model. Here we have this prompt: you are a critic, review the answer and share areas of improvements and suggestions. And then we generate a response and send it back to the model with the original task to generate a revised response. Here in this implementation, we are also passing retrieved context in the second call. So let's run this function by sending this query, which is refund policy exceptions. Basically, we are asking the agent to create refund policy exceptions. So here, as you can see in the first attempt, the model generated refund policy exceptions. These are the exceptions. And then it acted as a critique and criticized the first response in the second call. You can see it has strengths, areas of improvement. And then we retrieved an evidence which basically returned some documents from our knowledge source, which are similar to our task. And in the second call to the model, we get a revised refund policy exception, which incorporates the suggestions that were provided. So, this is the pattern that you can apply where you want to improve the quality of the agentic response. The third pattern that we will learn is plan and execute, which separates the strategic planning from execution. In this case, instead of deciding one step at a time, the agent first creates the plan and then executes each step in the plan in a sequence. This is particularly effective for multi step business processes and long running tasks because it provides visibility into overall strategy while the structured execution happens. Let us look at an implementation of this pattern. So, in this function that simulates an agent that implements plan and execute, we receive a goal to accomplish. And the process begins by passing this goal to the large language model and asking it to act as a planner. Given the high level goal and tools description, the model has to create a JSON plan which contains steps needed to accomplish the goal. We are passing this prompt to the large language model in this call underscore LLM call, and we have a plan that is returned to us. Once we have the plan, we load it into a JSON, and this JSON is basically an executable workflow that we can execute. So here you can see we have steps that we are iterating over, and for each step, we determine if an action needs to be performed. If it is, then we invoke the respective tool. In our implementation, we add the result of each tool execution to the trace so that we can observe it. Let's call this agent for this query: how are critical incidents handled? So, here in the first step, the model acted as a planner and it created a plan which consists of steps, which are mainly retrieval steps because we gave it retrieval function. It saw a need for retrieval and it is asking us to retrieve information related to definition of critical incidents, common types of incidents, etc. And then the executor executes each of these steps by invoking the retrieval function and extracting the documents. So, in this pattern, we saw a separation of responsibilities between the planner and the executor, which often improves reliability as it enables validation of plan before its execution. This makes complex tasks easier to manage. The next pattern that we will learn about is the router pattern, which is the simplest of multi agent orchestration patterns. In this pattern, we have a router or an orchestrator which analyzes the incoming request and classifies it as one of the multiple domains. It then directs the request to the most appropriate specialist agent for that domain. This pattern is very common in enterprise applications where different agents handle different specialized domains such as billing, support, technical troubleshooting, etc. Let us look at an implementation of this pattern. So the implementation starts by defining the router, which is basically this classify route method. It takes in the query and depending upon the keywords in that query, it routes it to specialist agents. In this implementation, a router can choose multiple routes. For example, if the question contains both refunds and approval policies, the question is sent to both the billing agent and the policy agent. And then we have implementation of the agents as these functions. In real world scenarios, each of these functions would be an actual agent. But here we have implemented these agents as simple functions that call the lookup tool with some text which is relevant to this topic. So if it's a billing agent, it's calling the lookup tool for refund policy, payment invoice, etc. We have this mapping of agents to the functions that we have defined above. And then we have an implementation of the agent itself, which implements the router pattern. So the agent receives a query, and as a first step, we classify the route using our router. And depending upon the routes that the query has been classified into, we invoke those agents. And as a last step, we gather the responses from each of the specialist agents and concatenate this response and send it to large language model for generating the final answer. So this is a very simple implementation of a router pattern. Let's invoke this agent using this query string, which is customer wants a refund and also asks whether manager approval is required by policy. So as you can tell, this will invoke both the billing agent and the policy agent. And here we see that the router classifies the request, and then both the agents are invoked, which basically retrieve some documents from the knowledge source, which is sent to the large language model to generate the final answer. So as you can see in the router pattern, the router acts as the classifier, dispatcher, and aggregator because it aggregates the response. Next, we will explore the tree of thoughts pattern, which is a search oriented reasoning pattern where instead of committing to a single line of reasoning, the agent explores multiple possible approaches. It evaluates them and expands the most promising options. This technique is very useful for complex decision making tasks or planning and optimization tasks where multiple strategies may exist. Let's see an example implementation to understand this better. So here we have two functions, generate thoughts, which basically generates different thoughts or different strategies for a given problem. So here, if you notice the prompt, it says generate three fundamentally different business strategies for the problem. Base your strategies on the following context and return only JSON with strategy colon and each strategy. And then we have a different function for evaluating these strategies to find the winning strategy. So here we have the prompt, which is the problem, strategy, and evidence, which is basically documents that we retrieve from knowledge source. We're asking it to score the strategy between 1 to 5. In this function that simulates the agent that implements tree of thoughts, we are getting a problem And as a first step, we are generating different strategies by calling generate thoughts. So we will get three strategies as a result of this. And then we load these thoughts as a JSON. Then we iterate over each thought and we evaluate each thought to get a score. If you remember, we asked the model to give us a score. We then find the winner by finding the strategy that has the highest score. So let's call this agent by sending this query, which is what is the best expansion strategy for our business in European markets? So the agent first received the problem, and as a first step, it retrieved the two documents we have on European investment trends and Europe AI trends. And then it created three strategies, which are enterprise centric AI solutions expansion, regulatory compliance as a service, and AI driven SMB empowerment. And then we passed them to the evaluator, which basically scored two strategies as four, and we picked one of these strategies. In this final section of the lab, we will focus on multi-agent coordination patterns. And the first pattern that we will learn about is the hierarchical pattern, where a supervisor agent receives the task and decomposes it into subtasks. It then delegates the work to specialized agents before it synthesizes the results. The supervisor agent provides centralized control and governance in this pattern. If this sounds very similar to the router pattern, then the key difference here is that router only forwards the request to specialist agents and aggregates the results, whereas a supervisor not only decomposes the request and submits it to specialized agents, it also actively manages the execution by validating the results and coordinating the revisions with specialized agents. This results in improvement in the overall answer quality. Let us look at an example implementation of this pattern to understand more. We have mock specialist agents that are implemented as these functions. We have this function called specialist agent, which contains the common logic shared by all specialists. First, it retrieves domain specific information from the knowledge source, and then it creates the prompt by combining the knowledge and the customer query. It uses this prompt to generate a response from the large language model. Notice that we have revision request parameter, which allows the specialist agent to revise its response based on feedback from the supervisor. This is what differentiates a supervisor pattern from a simple router pattern. A router only decides where the work should go, whereas supervisor actively reviews the work and helps improve the quality by providing feedback. Now, this common implementation is used by each of the specialist agent, as you can see here. And then we have a mapping of agent names to their implementation functions, followed by the classify route function, which is similar to what we saw in the router pattern. In a production system, the supervisor might actually decompose the task into subtasks rather than simply classifying it. However, to keep this example simple, I'm using the keywords based classification as I did with the router pattern to determine which specialist agents should participate. And then we have the supervisor agent, whose responsibility is to review the outputs that are produced by the specialists and then use a large language model to determine whether any information is missing or incomplete. And this is the orchestration code that ties everything together. It accepts the user query and uses this classify route function to classify it to determine which specialist agents should be invoked. It then invokes each agent and gathers the output in this outputs list. It then passes the output to the supervisor agent for evaluation. If the supervisor agent indicates that a router agent has to revise its response, that router agent is invoked with the revision request. And then in the end, all the responses are combined together to create a final response using a large language model. So, in this example, we see a clear hierarchy between the supervisors and the set of specialists. Specialists focus on solving the problem, while the supervisor focuses on evaluating and improving the quality of the solution by providing the revision requests. Let us invoke this agent by using this query, which is customer wants a refund, also asks whether manager approval is required by the policy. So, as a first step, the supervisor plans and delegates this request to billing agent and policy agent because we have refund and policy words. And then the billing agent produces a response using a large language model. Now, prompt was very generic, so we have a lot of response, but you can see that we have this text which is from our knowledge source. And then policy agent also generates a response. And then the supervisor agent has a review which says the billing agent needs revision. It needs to explain refund eligibility criteria, including specific conditions or exceptions beyond 30-day window or platinum customer status. The supervisor assigns this request to the billing agent and it has a response. You may feel that the response has a lot of data which is not needed to answer the question, but that is because our prompts do not restrict the model from generating beyond what is provided to it. And also, we don't have enough data in our knowledge source. But the key idea here was to see how supervisors and agents can work together. The next pattern that we will learn about is the collaborative blackboard pattern, where multiple agents communicate indirectly through a shared state by reading and contributing information to a common workspace rather than communicating directly with each other. Let us see an example implementation. So, here in this example, the process begins by defining a shared data structure called the board or a blackboard. In this example, we have a researcher agent that analyzes the task and adds the relevant finding to the board. The planner agent reads the information and contributes the proposed plan in the board, and then the reviewer agent examines the accumulated work and adds its risk assessments, validation checks, approval requirements, etc. Notice that agents do not need to call each other directly, and the collaboration happens indirectly through shared Blackboard. This approach simplifies coordination and it allows for asynchronous collaboration. And the last pattern that I want to discuss is the swarm or decentralized handoff pattern, which is a multi agent approach where many autonomous agents work towards a common goal without a central coordinator or supervisor, as we saw with the hierarchical pattern. Each agent follows simple rules, shares information with its peers, and collectively they produce an intelligent global outcome. This idea is inspired by natural systems of bee swarms or ant colonies, where no single member controls the group, yet complex behavior emerges through collaboration. The idea is popular, while pure swarm architectures are still relatively uncommon in production AI systems because of the complexities of managing a decentralized system. This architecture is popular in AI research, simulation environments, any distributed problem solving, or autonomous code agents. And this concludes our lab, where we learned various patterns that form the building blocks of agentic AI implementation. By understanding when to use React, reflection, planning and execution, routing, multi agent coordination, you can build intelligent systems for your specific use cases. Modern frameworks such as LangGraph, GrooveAI, AutoGen, etc., provide built in support for many of these capabilities. So you can focus on your business logic rather than worrying about the implementation details of these patterns.